Hello everyone, my name is Jahandardoost and I will talk about the potential induced degradation and recovery effect on CIGS, CDS solar cells with the sodium and rubidium treatment. So the objective of this work is to investigate the effect of the alkali treatment, mostly sodium and rubidium fluoride, on the potential induced degradation for CIGS, CDS solar cells. We're comparing the PID effect at different temperature, and also be looking at the recovery of the CIGS devices by reversing the polarity of the voltage bias. We used 4 different types of the device in our experiment. Type 1 is the baseline device. Type 2 has the sodium oxide barrier before the molybdenum back contact to prevent the sodium diffusion inside the CIGS cells. Type 1R is the same as the type 1 with the rubidium fluoride post-deposition treatment, and type 2R has the same structure of the type 2 with the rubidium fluoride post-deposition. All the CIGS cells went through the same process of the cell growth for the CIGS and chemical bath deposition for the cadmium sulfide buffer layer. Then all of them have the intrinsic zinc oxide and zinc oxide aluminum window layer, and finish with the nickel aluminum nickel grid at the top. To prepare the cells for the PID, we put the cells inside the PVC plate, and we use the silicon sealant to secure the cells inside the PVC. We use this process to make sure there is no leakage current between the top wire and the back wire, and also there is no arc between these two wires because they are so close to each other. We use the aluminum foil to connect one of the wires to the back of the glass to make sure that we have the uniform distribution of the voltage in the back of the glass. Then we put the prepared cells inside the oven to reach the temperature during the PID and also recovery of the cells. We applied the 1000 volt during the PID, and the positive pole was back of the soda lime glass, and the negative side was the molybdenum layer. And during the recovery, we reversed the polarity and applied the positive pole to the molybdenum back contact and negative pole of the voltage to the back of the soda lime glass. We performed the PID and recovery at 25, 85, and 65 degrees centigrade. So the behavior of the cells before the start of the test at the T0 according to their content, sodium content and rubidium treatment, we observed that the sodium increased the performance of the cells due to the higher open circuit voltage and fill factor. Low sodium devices, both with the rubidium and without the rubidium, show a slightly higher band gap due to the increase in the gallium diffusion in CIGS cells. And the efficiency of the devices with the rubidium treatment didn't show any improvement compared to type 1 and type 2. During the PID, we observed that the leakage current increases exponentially by temperature. And also we observed that with the higher temperature, we see the higher degradation with the same amount of the charge accumulation inside the cells. Also for the PID, for 4 different types of the cells, type 1 with the rubidium treatment or type 1R shows the smallest amount of the degradation compared to 4 other cells. and type 2 shows the highest amount of the degradation. After the recovery, we observed that the higher temperature led to the higher recovery rate for all devices, and the baseline cells showed the same recovery rate for the 65 and 85C according to the charge accumulation. Low sodium cells or type 2 shows the highest amount of the recovery at 85, and the recovery of this cell was higher from the baseline or type 1. Rubidium treatment of the type 1 improved the efficiency of during the recovery of the cell. Rubidium treatment of the type 2 or type 2R caused a different behavior on the recovery according to the temperature, and we observed a higher recovery at 65C. And all devices reached the saturation point after 500 hours of the reverse bias at all temperatures. In conclusion, we observed that the leakage current increased exponentially with temperature for the same PID voltage between the glass substrate and molybdenum back contact. Charge accumulation is not the only factor for the PID degradation, and higher temperature increased the degradation for the same amount of the charge accumulation inside the cells. Degradation behavior at higher temperature and 1000 volt bias is similar for all devices without the consideration of the sodium or rubidium content inside the cells. All device type recovered their efficiency partially after reversing the voltage bias and changing the polarity between the soda-lime glass and back contact. And rubidium treatment has a small effect on recovery rate for device with the baseline sodium compared to device with the low sodium content.